So, in the name of Allah, the most merciful and most beneficent, today in our lecture 5 in pure mathematics, we are going to start linear algebra. Previously, we discussed real analysis and we ended it, I think, within 2 lectures. And now we are going to start linear algebra. So, basically, we will be doing what we call the fundamentals of linear algebra and then advanced linear algebra. And the main topic in linear algebra is going to be what we call vector spaces. But right now we are not going to define what a vector space is, but we are only taking our favorite vector space Rn and we call it Euclidean space or Euclidean vector space. What is a vector space? We will be defining maybe after a few topics, but right now we are considering our favorite set Rn and we consider it to be a Euclidean vector space. Now I have written Rn, it means we are going to generalize our discussion of R1, R2, R3 and so on. Rn is going to be the fixed dimension for this vector space, that is going to be n. So if some V belongs to this Rn, then what is the shape of V? So if I take any vector in my vector space Rn, then what is going to be the shape of this particular vector? So this is going to be, let's say, V1, V2 up to Vn, and I think we call it n-tuple. N-tuple. Okay, so we have a vector space Rn, so this is what we call vector space. So simply it is a space which contains so many vectors, and the element that belongs to this vector space is called vector. And we know very well what does a vector represent. Okay, it represents some sort of length as well as what we call the particular direction. So we know very well that when we take R1 and R2 or R3, we can visualize these all the things geometrically, but if we take beyond R3, we cannot give exact geometric representation for that. We have some sort of geometric representation for R4 as well, using basic fundamentals in physics what Einstein did. Like we have 3 dimensions x, y and z, and the 4th dimension is going to be time. So basically time is going to foliate your space. So it is going to be, okay, at time 0 you are here, at time 1 you are here, at time 2 you are here. So you are going to create different spaces within a single space. So that's another idea. But geometrically we can represent only R1, R2 and R3. And Rn is going to be the generalized notion. And why we are studying Rn? Because in Rn we can solve so many equations. So many real life problems in optimization in other fields involve variables more than 3. 4 variables, 5 variables, 6 variables. So to deal with those problems, we need a generalized theory, what we call theory of Rn. So this is the particular structure of this vector in Rn. So this is our vector space, and the element, any element if we pick from this particular set, we call it a vector. Now what we can do, we can define, okay, what is the length of this vector? What is the length? So length is what we call the norm or magnitude, and sometimes we give these 2 lines on either sides. What is the difference? Why a single line and why 2 lines? In R1, R2, R3, even in Rn, the single line will work because we know very well what do we mean by the length of a vector. But in any generalized vector space, length is a different idea. Okay, for example, you are taking a vector space of continuous functions, the vector space of the functions which are differentiable ones, then how you define the length of that particular thing? Then you always define the norm of that, because norm is going to be the generalized notion for length. And for definition, either I will write this thing, or whenever you see these 2 signs with DEF written on the top, we call it definition. So it depends upon the notion that we use for. So what is the norm of this particular vector in Rn? That is simply v1 squared, v2 squared up to vn squared and the positive square root of that one. So then we can say that okay, this is a norm function on Rn, whatever our vector space is, and then we define some properties. Okay, the norm is always a non-negative, it means it is 0 or greater than 0, and if the norm is 0, the vector itself is 0, it satisfies some properties, then we call this particular thing to be a normed space after satisfying some certain properties. But we are not going in that detail, we will be doing later on when we are doing function analysis. Okay, so this is how we define the norm of vector, and you have another vector, let us say w, with the components of the vector to be w1, w2 up to wn. Then how you define v minus w? That is just component wise subtraction, v1 minus w1 and v2 minus w2, and it is not necessary you write this thing in detail. You can say that okay, you have a vector v with some sort of components vi, where I runs from 1 to n, and you can write this thing. And if you want this, you can write in compact form that it is vi minus wi, where I runs from 1 to n. So it is going to be v1 minus w1, v2 minus w2, v3 minus w3. So it is just a compact form to write these things. Otherwise, it is not necessary to write in this particular form.
Can't we write in this same notation? Just like you are writing v.
There is a problem with this notation, that it is an ordered pair. Then you have to show the position of each and everything. It is not clear from here that it is going to be some sort of ordered thing. So it is better not to write in this way. You can write some other elements in this way. Okay, you have some vectors, and now I am taking some vectors. v1 is a vector, v2 is a vector, and vn is a vector. Then I can write okay, I have a set of vectors. It is good thing, you can write in this way. But this is a single vector with these components, so it is better not to write, but okay, for compactification we can write it in this way. Okay, so we are going to build the theory that what we need so far, and then we will be doing the things later on. And then we can actually define what do we mean by the sum of two vectors, because sum and subtraction are going to be the counterpart of each other. And then we can also define how can we scale a vector with some constant c, and this c belongs to the set of real numbers. We can take this c to be in the set of complex numbers, but since we are in real Euclidean spaces, so we are only concerned about the real numbers. So what is this thing? This is cv1, cv2 up to cvn. So we are going to scale each and every component of this one. Then there are some certain properties of this particular Euclidean vector space Rn, that if you add two vectors and if you change their order, the result is always going to be same. We say that addition is commutative in Rn, and so on. So there are lots of properties, but we will be dealing with these properties when we are coming to define what a vector space is explicitly. Okay, so we are going to just build the theory that we need so far. Okay, so we have a set of vectors. Now I have some vectors vi, where I runs from 1 to n, and these are the vectors in Rn. It means if you take a vector v1, now it's not a component, it's a vector. So what is the form of this? It has exactly n components, and I can name these components to be, let's say, v1 up to v1. Now I am going to say this is the first component, this is the second component, and this is the nth component. So this is just a notation. I am taking some vectors in Rn. So what do I mean by linear combination of these? Linear combination of these VIs. So what do you mean by linear combination? I have some vectors in Rn, and let us take some Ci's in R. So this is your vector space, and this is the field on which your vectors are defined. This can be R, this can be C, or whenever you write a generalized K, it means it can be either R or C. Both will work. But right now we are concerned about R. So you have some vectors, you have some scalars. The linear combination of these vectors is defined to be C1 V1 plus C2 V2 up to Cn Vn. This is going to be the linear combination of these n vectors when these are scaled by some n scalars C1 to Cn. So this is the definition. So we are going to build the theory, so we have to do these things bit by bit.
So what I understood that we make it correct. Linear combination means a vector, there's some components, and they are connected with any scalar, or scalar can be single or many, can be scalars so many times different.
Yes. These scalars can be like any real numbers. Any real numbers. These can themselves be zero as well. If these all the scalars are zero, you will get a null vector. It means when you take the linear combination of these all the vectors with some scalars to be zero, you get a null vector and so on.
But sir, please make it correct. In the last step from the left hand side, you have done the C multiply, where C is a fixed scalar.
C is a fixed scalar.
But here C1, C2, C3, all are different scalars. So
yes, the problem is you are mixing these two things. What is V1 here?
there's fixed number, C is a fixed.
What is V1 here?
The component of
It's a component of vector V.
Okay.
What is V1 here?
It's a component of V.
It's a vector V.
It's a vector.
It's a vector V.
It's a field.
So that's the difference. It means I want to explain you
Counter example, sir.
in not counter example, the simplification of this one.
Okay.
I have some vectors V and W. Now I am not writing V1 and V2. I am writing V and W. These are two vectors. And what is the form of this vector V? You know very well, it is V1, V2 up to
Fine.
Vn. What is the form of this vector? W1, W2 up to Wn.
Fine.
Now I am going to take the linear combination of these two. What I will do, I will scale V by some scalar C1, scale W by C2 and take their sum. This is the linear combination of these two vectors. So here V1 is a vector, there V1 is a component.
It's a generalized form with so many vectors you have given.
Yes. Inside this V1, there are exactly n components. Inside V2, there are exactly n components. So you can see, I have not enclosed this with a bracket because this is a vector itself, this is a vector, but these are components. Component. So I enclose in some sort of bracket. So this is a vector itself, but these are different vectors. V1 is a different vector, V2 is a different vector.
Which contain inside so many components.
Yes, n components exactly. N components.
We are taking some vectors, scaling them, then we are going to
Yes, some sort of vectors. We are going to scale these with some numbers, and then we are going to add these. Okay, this is what we call the linear combination. We will be using this in our further discussion ahead. So for example, I am taking some vectors. For some simplifications, I will restrict my attention sometimes to R3 as well, or R2. So in R3, I am taking three vectors: 1, 0, 0, 0, 1, 0, 0, 0, 1. I have these three vectors. Okay, now I want to define a linear combination for them. So, first of all, I am going to name this vector to be V1, this vector to be V2, and this vector to be V3 in this way: V1, V2, and V3. But I am going to call these E1, E2, E3 because of some reasons. Because when we will see, these are called the standard bases in R3. Okay, so I am going to name these in this way. So I have a vector A, B, C, any vector. Can I write this in the linear combination of E1, E2, E3?
One is at A count.
Yes, yes. It means E1 should be multiplied with A, E2 should be multiplied with B, and E3 should be multiplied with C, and then added, then we'll exactly get ABC. So if you have any vector like this one in R3, this is any vector because ABC is not fixed. If you have any vector in R3, you can always write that vector is a linear combination of these three vectors, what we call a standard basis of R3. So you can see we have a notion of linear combination, and now we are going to use it. And what do we mean by linear combination?
So ABC here what a constant or a vector?
ABC are itself real numbers, but when you write it in three tuple, it becomes a three-dimensional vector. It's any vector. ABC is not fixed.
Every vector have a linear combination.
Every vector in R3 can be written in the linear combination of these basis vectors. These basis vectors. Any vector in R3.
Well, here ABC is a vector, but ABC itself they are a component of that vector.
ABC
Or the
are the components.
of a single vector.
Yes, yes. Now, if I say that, okay, in R2, what happens? You have E1 to be 1, 0. You have E2 to be 0, 1. You take any vector, it can always be written in this form. A E1 plus B E2. But we call this the standard basis for R2. So this is basis for R2. We'll be defining what do we mean by basis, but right now, okay, consider this to be the basis. Now, I want to do one thing else. I give you two vectors, E1 and E2, and let's say the vectors are 1, 1 and 2 and a 2. I want you to write this vector in the linear combination of these E1s and E2s. Is it possible? The first problem is I should not write E1 and E2 here because these are not standard bases. But I am writing for the moment just to understand the idea. That you have two vectors in R2. Now I want to ask you a question. Can you give me some scalars C1 and C2 that when I multiply with E1 and E2, my answer is going to be this vector?
Scale is negative or C1.
It is not possible. It is not possible. Hence we call that this is not a basis for R2. If you write any vector in R2, any vector means I can choose any vector. Not 2, 3, I can choose any vector. And I am giving this as a counter example. So you can write any vector as a linear combination of E1 and E2. Then you say that okay, E1 and E2 makes the basis for R2. But this is not possible because I have given you a counter example right now. You can make a system and you can solve it, and you will see that the determinant is going to be 0. So the matrix is invertible, not invertible. So you are unable to solve with some sort of methods. So you will get a system.
That if we see the like negative number or putting some sort of a fixed number,
Yes.
that approximately
The answer is going to be 2, 3, but it is not possible. It is not possible. I want you to solve this system now. Solve this system. C1, what is E1? 1, 1. C2, what is E2? 2 and a 2. So make a system. C1 times 1 is, let me write here, C1 plus 2C2 equals 2. And this is C1 plus 2C2 equals 3. You can see these are some parallel lines. When you take C1 and C2 to be X and Y, these are parallel lines and no point of intersection, hence there is no solution. Okay, so this does not make a basis for R2.
So matrices में सर क्या आइडेंटिटी हो गया ना, और कैसा मल्टीप्लाई में सब वो चीज़ डाल ले, matrices में आइडेंटिटी है कि बेस नहीं है
Yes, yes. It's the same thing. It's the same thing. Because we'll take this Euclidean vectors and then we'll convert these things into matrices as well. Okay, a few next ideas. So you have V and W to be already defined in Rn. What do you mean by this particular thing? What we call this? The dot product. We call this dot product. How do you define it?
Corresponding.
Take the first component V1, first component W1 multiply V2 W2, V3 W3, and then add these all. This is going to be the dot product. So in compact form you can write it Vi Wi multiplied, and you take their sum from 1 to n, and this is by definition. And if we say that V dot W is norm of V, norm of W, and cosine of theta between them, it is not the definition. The definition is this one. That's going to be the alternate formula we proved already in, I think, multivariate course. Okay, then we can define the norm of vector that we have already done so far, but we can relate this that if you have vector V, its norm is exactly same as take the dot product of V with V and take their square root. Is it right? Always. So you dot product V and V, that becomes V1 square, V2 square, up to so on, and take their square root. This is exactly the norm of V. And we will see that this is a norm that comes from the inner product. There is an inner product that comes from the norm, then we can relate some ideas, because sometimes we call these, not sometimes, always we call these normed spaces, and we call these inner product spaces. And if the norm is complete, we call it Banach space. If the inner product space is complete, we call it a Hilbert space. So we are going to connect the idea, okay, what is the connection between a Banach space and a Hilbert space. Later on we will see. Okay, I give you a vector. Sometimes they write in this way to denote a vector, because otherwise you will be missing the idea. So you should better write in this way. And these are the components, so I should not give an arrow because these are the scalars. I have a vector in Rn. What is going to be the norm of this one? I don't know, but I can find it out. I want you to give me a vector from this W whose norm is 1. It means I want you to normalize this vector. How to do it? So normalize this vector means just take W and divide with its norm.
Each component.
Yes, each component, because this is a scalar. And when you will take norm again, this will always be 1. And what we call this? It's a normalized vector. A normalized vector. And we can do these things. And maybe we'll need these things so many times.
So you are defining norm there.
Yes.
V dot V, right?
It's not definition. It's just a formula that connects these two things.
If
We know very well what is the definition of norm. That's V1 square, V2 square. But I am going to just connect norm with inner product. It's not definition, this is a formula that connects these two. You can sometimes call it definition, no problem. Okay.
Unit vector and normalized vector we do.
So unit vector is itself a unit vector. But normalized vector means you have a vector which is not having unit length, but you are going to normalize it. Then you call it that it was not a unit vector in the beginning, but you did something, now you got a normalized vector. It's a unit vector. It's a unit vector. But normalized vector is the name which is assigned because we are going to make it normalized by ourselves. Otherwise it's a unit vector. Sir, sir.
Sir, आपको जब v और dot का multiply करेंगे ठीक है component wise ये v dot तो आंसर v को vector ही दो या आपको scalar ही दो
This one.
dot product
Always scalar.
always scalar
Always scalar.
वो सही है वो vector मान लीजिए नौ vector generate नहीं
No.
dot product scalar ही दो
Dot product it's a scalar. because Vi is a number, Wi is a number. You multiply two numbers, you get a number, and you add these all the quantities, you still get a number.